The next problem to consider is consistency of the state estimator for a dynamic system. Filter consistency. When we're estimating a parameter which is constant, the definition of consistency for such a static estimator was convergence of the estimate to the true value. This implies that there is a steadily increasing amount of information in the sense of Fisher about the parameter we are estimating, which eventually asymptotically will reduce to zero the uncertainty about its true value. When estimating the state of a dynamic system, because it keeps varying, we cannot expect convergence of the estimate. What we have is a current estimate, x hat kk, and an associate covariance matrix, pkk. First, before discussing consistency, which is the counterpart of convergence, we'll take a look at the opposite of convergence, that's divergence, because historically it has been observed that the filter used to yield in some cases unacceptable large state estimation errors. And this can be due to one or more of the following reasons. You can have modeling errors, you can have numerical errors, and last but not least, you can have programming errors. The question of what an acceptable estimation error will be from a statistical point of view is what we are going to discuss in detail next. If we are operating under the linear Gaussian assumption, the conditional PDF of the state at time k, p of xk given z super k, is Gaussian with argument xk, mean x hat kk, and covariance pkk. What we do to obtain this estimate and covariance, we use a system model that consists of dynamic equation, the measurement equation, and the statistical properties of the random variables entering into these equations. Again, that's the initial description of the state, its initial PDF, or mean and covariance, the process noise, moments, mean 0 and covariance, and the measurement noise, mean, again, assume 0 and its covariance. If all these are completely accurate, then this density holds exactly. However, we have to recognize that all models contain some approximations in practice. Therefore, we would like to see to what extent we can verify this in a practical manner. So, the practical evaluation of consistency is as follows. What we do is we design a filter based on statistical characterization of the disturbances, which is done with moments up to second order. And then we hope that the resulting filter will give approximate first and second order moments of the state. We will use the first moment condition in a slightly different fashion, essentially saying that the mean of the error is 0, which means the estimate is the conditional mean of the state, and the covariance of this state, or the covariance of the estimation error, is as calculated by the filter, namely pkk. In other words, the filter should satisfy the two moment conditions in spite of inherent unavoidable approximations. The first condition is really the unbiasedness requirement for the estimate, 0 mean estimation error, while the second is covariance matching requirement, namely the actual mean square error. This is the actual mean square error because this is not an exact conditional mean, will be an approximate estimate. That's the expression on the left-hand side, matches the filter calculated covariance. So this will be our main demand, main expectation from the filter, that the covariance calculated by the filter is realistic. It matches the actual errors. Now, if there is a bias, this will clearly increase the mean square error, which would be the bias squared plus the variance in the scalar case. Thus, the test that we are going to work with will deal only with the mean square error. If it is satisfied, okay. If not, there can be two reasons. One, possible bias. Second, incorrect variance. And we hope that the results will be positive, so we don't have to go into the more detailed evaluations. So the test will be based on the fact that under the linear Gaussian assumption, we have the expected value of x tilde transpose P inverse x tilde, which is under our assumption, again, because x tilde is Gaussian, pkk is its covariance, this quadratic form is chi-square with nx degrees of freedom, the dimension of the vector x, therefore its expected value is nx. So the average of the squared norm of the estimation error has to be equal to the dimension of the corresponding vector in view of the properties of the chi-square distribution. Now, why are we so concerned about consistency? It's not just honesty, there's more to it. Since the filter gain is based on the filter calculated error covariances, it follows that consistency is necessary for filter optimality. If the filter puts out wrong covariances, you have the wrong gain, and this degrades the quality of the estimation. That's why consistency evaluation is vital for verifying a filter design, because what it really does, it evaluates estimator optimality. Now let's go and define the quantities to be tested and present the tests for filter consistency. We'll say that a state estimator is consistent if the estimation errors satisfy the two first and second order moment equalities in these equations given earlier. Now, this is a finite sample consistency property, that is, the estimation errors based on a finite number of samples, measurements, should be consistent with the theoretical statistical properties of having zero mean or having unbiased estimates, and the second one have covariance matrix as calculated by the filter. In contradistinction, the parameter estimation consistency is an asymptotic, an infinite size sample property. Here we will be concerned always in a finite number of samples to have these two properties found acceptable for statistical test. So, the consistency criteria are as follows. The state errors should be acceptable as zero mean and have magnitude commensurate with the state covariance as calculated by the filter. The innovations should also have the same property, and the innovations should be acceptable as wide, because this was one of the important properties we have shown for the innovations. The last two criteria are the only ones that can be tested in applications with real data. You don't have ground truth, you don't know the true state, there's no way to do A. In some special cases, you can have a close enough to ground truth with special, very expensive instrumentation, but typically a real-time filter will have to rely in its tests on the innovations, because they are always available. Even though the most important is really the first criterion, but that is, for obvious reasons, available only in simulations. Now, we'll use the notation again as before. X tilde is x minus x hat, and we define the normalized state estimation error squared, NEES, normalized estimation error squared for the state, as epsilon at time k is x tilde kk prime, pkk inverse, x tilde kk. So this is a quadratic form, which again is chi-square distributed nx degrees of freedom, and this is for a certain time k. And if this has the appropriate behavior, it is within statistical limits that we are going to derive in a short while, then we can say that the estimate is both unbiased and its covariance is compatible with the actual magnitude of the errors. So it can be used to verify both properties 1 and 2. Under the hypothesis, the null hypothesis H0, that the filter is consistent, and the linear Gaussian assumption, epsilon k will have a mean nx, because it's nx degrees of freedom chi-square. So what we want to see, can we accept that the mean of epsilon k is nx? Obviously, from a single run, you cannot say very much, even though we can make some statements, but will be hard, as you'll see later. So what we are going to do is Monte Carlo simulations. The test will be based on a number of runs with independent random variables. This is the essence of Monte Carlo simulations, that provide n independent samples of epsilon k, denoted as epsilon I of k, of this random variable epsilon of k. Then we will look at the sample average of epsilon k, which is epsilon bar of k, that's 1 over n, sum I1 to n of epsilon superscript I at time k. So this is the n-run average, NES, normalized estimation error squared. Putting this n from the denominator on the right-hand side to the left-hand side, we have that n epsilon bar will have under H0 a chi-square density with cap n times nx degrees of freedom, because each epsilon ik is chi-square with nx degrees of freedom, and they are independent because that's the essence of the Monte Carlo runs. They are all using completely independent random variables. Therefore, and the sum of chi-square degree so freedom just adds the sum of chi-square distributed random variables that are independent results in another chi-square with the total number of degrees of freedom equal to the sum of the degrees of freedom of the components. So you have n times nx degrees of freedom for the n epsilon bar, and our hypothesis that the state estimation errors are consistent with the filter calculated covariances, which we also call a chi-square test in view of the distribution used, will be accepted if epsilon bar is in some interval R1 to R2 called the acceptance interval, and it is determined such that the probability of epsilon bar to be in this interval under the null hypothesis that the filter is consistent will be a number close to 1, namely 1 minus alpha. And here's an example. If alpha is 5%, we have a two-dimensional state. We carry out 50 independent Monte Carlo runs. What we have is R1, the two-sided interval for a 50 times 2, 100 degrees of freedom chi-square, is between 75 and 130. Divide everything by 50, you end up with R1 as 1.5, R2 as 2.6. So this is the two-sided 95% probability concentration region for epsilon bar. This is where epsilon bar from 50 samples should be. If it is in this interval, yes, we accept the null hypothesis that the filter is operating properly. If it is outside, we reject it. Obviously, this is subject to the allowable 5% error probability, namely we are going to reject H0 with 5% probability even though it might be true. So we have to always think that we cannot have a perfect test under uncertainty. The statistical test will be subject to some small allowable error probability. Now, if we have a single run n equal 1, you can also use this test. In this case, the two-sided 95% interval, in this case, for a 2 degree of freedom chi-square, you can look up in the tables at the end of chapter 1, is 0.05 to 7.38. What is important to know, the much narrower range of the interval based on 50 Monte Carlo runs, because what Monte Carlo runs do, they reduce the variability, significant variability reduction by repeated independent simulations. So we have a lot more confidence. It has to be in a much narrower interval. Now, as indicated before, a bias in the state estimation would increase our normalized estimation error squared, and if significant, it will yield unacceptably large values for our statistic. Now, if the epsilon bar is not in that acceptance interval, it's 95% probability concentration region, then a separate bias test using the sample mean of the state error should be carried out to identify the source of the problem. This can be done by taking each component of the state error, divided by its standard deviation, which makes it under ideal conditions Gaussian with zero mean unity variance, and testing to see if the mean can be accepted as zero. So what we have is a separate subtest if the first one is not accepted to identify whether the problem is in the mean or in the variance. Typically, if you have a problem, it could be in both places. And here is the test. The test statistic for the normalized mean estimation error, and MEE for the jth component of the state from n runs, will be 1 over n, sum I from 1 to n of x tilde I output or error vector in run I sub j, that's component j, k given k, divided by the square root of the corresponding variance pjj, so divide by the standard deviation. And because this is Gaussian with zero mean unity variance, you take n such independent variables, add them up, divide by n, the result will be, under ideal conditions, mean 0 and variance 1 over n. If we denote by zeta, or psi rather, sorry, zero mean unity variance normal random variable, let R1 be such that P of psi in the minus R1 to R1 interval is 1 minus alpha. Again, that's a number close to 1, typically 0.95 with a 5% error probability allowed. Then, since the standard deviation of mu bar j is 1 over root n, the 1 minus alpha probability region for this mu j bar will be minus r to plus r, where r is r1 over root of n. So with r1 for 95% being approximately 2, r will be 2 over square root of n. So then we have directed the acceptance region, now based on the normal density of the hypothesis that the true mean is 0, mu j has to be in the minus r to plus r interval. Mu j bar, this is from n runs. the commensurateness of the innovations with their filter calculated covariance as a second criterion is tested in a similar manner. And for this we have, under the hypothesis that the filter is consistent, namely innovations are zero mean and with the calculated covariance, is the normalized innovation squared, NIS. That's epsilon sub nu, nu prime, S inverse nu, again because of the Gaussian assumption, would be chi-square distributed with nz, degrees of freedom. Remember, innovation has the same dimension as the measurement, so dimension is nz. And from n independent samples, epsilon sub nu superscript I, we calculate an n-run average, normalized innovation square, and epsilon nu bar is 1 over n, sum epsilon nu I of k, I from 1 to n, which has exactly the same kind of test, except that now the n epsilon nu bar is chi-square distributed with cap n times little n sub z degrees of freedom. So, except for the change of dimension and number of degrees of freedom, we have essentially the same test. The next test will be the third one for whiteness. It's somewhat complicated to do a whiteness test on a vector, so it can be done on a single component at a time as follows. We have an n-run sample autocorrelation statistic. Rho L bar kj, we take 2 times k and j, component L of the innovation in the run number I. So the summation is over I from 1 to n, the number of runs, and we divide by a sample variance. You can divide by calculated variance. I think it's probably more appropriate in this case to divide by a sample variance, because it's easy to calculate. For large enough n, this quantity can be approximated as having a normal density for k different than j, and the mean of that will be 0, because ideally it should be 0 for any k different than j, and the variance is 1 over n. So with this, we have the third test for the whiteness on a component by component basis. Now, up to now, all these tests assume that we have the luxury of n independent runs. While this can be done on a single run, as we have seen, there is a very large variability. So, the question is, can one achieve low variability on a single run? That is the point. In real time, we have only, say, 1 run available. So now, if we can do it on a single run, we have a practical real-time consistency test. Now, the test on the normalized estimation error square for the state requires really independent simulations. There is no way to get around that. However, criteria B and C, this is the normalized innovation square, this is the whiteness of the innovation, can be tested on a single run as follows. We can replace the ensemble averages. Remember what we had, if you test the normalized innovation square, you want the expected value to be according to the calculated covariance, or that chi-square quantity, chi-square statistic, should have a mean of nz, and over n runs should have the sample average, a mean of nz, and with a fairly narrow variability region around that mean. Now, what we want to do is, instead of a statistical average, which is done by many Monte Carlo runs, or expected value, so that's an ensemble average, we are going to replace this with time averages based on the ergodicity of the innovation sequence. Ergodicity is the property of a stochastic process that a long-term time average gives the same result as a statistical average. Has to be stationary. Now, for innovations, the whiteness statistic from a single run with j steps apart, this will be a time average autocorrelation. So L steps apart, rho bar, this is the product, nu L times at k times nu L at k plus j. So this is all component L, and here we divide by the sample variance. So if you notice here, there's a sum of k terms times another sum of k terms, which is really k square. Square root of this ends up with a k out here times the variance. So we really divide this, there's an implicit division by k here. Therefore, for large enough k, in view of the central limit theorem, this will be Gaussian, and its variance will be 1 over k, is discussed in one of the problems at the end of the chapter. And we could write, but it's more complicated, a single statistic that incorporates the entire innovation vector. The second criterion, B, can be tested with a time average normalized innovation square statistic. Epsilon nu bar is 1 over k sum k1 to cap k, nu k prime, sk inverse, nu k. So this is the quadratic form for the normalized innovation square at time k. We sum over k points in time and divide by k. And again, because of the whiteness, we're assuming that the whiteness condition is satisfied, this will be the sum of cap k independent chi-square random variables with nz degrees of freedom. So the resulting sum has chi-square distribution with cap k nz degrees of freedom. We divide by cap k, so we will be based on this distribution, but divided by k, so we'll be around nz. All these numbers end up to be around nz. And the probability regions for these tests based on these distributions are set up exactly as before. Some examples of how we can reach a conclusion on the filter consistency, which amounts to, is this filter operating properly in a statistical manner, will carry out the following tests: offline single run simulation tests, offline multiple run, that's Monte Carlo simulation test, and online single run or real-time test. In real time, all you have opportunity for is a single run, and at any time you are asked, you should be able to give an answer. And what we are going to illustrate is a filter which is based exactly on the same model as the process, matched to the system, optimal, and the filter which is based on a different model than the system, it's mismatched, therefore it is a suboptimal filter, and we are looking for the test statistics to tell, in the first case, yeah, it's operating okay. Second, no, it is not operating okay, there's something wrong with the filter, in this case, the design. The single run simulation tests will be shown, the figure 5431. The behavior of the state's normalized estimation error, that's offline, for various values of the process noise variance for filters that are perfectly matched. Because this is a 95% region, 3 to 6 points are found outside. Before looking at the picture, we'll see how the probability region was obtained. The upper limit of our region is approximately 6. We took a one-sided, we cut only the upper 5% tail, so that's about 6. If we use 2.5% from above, 2.5% from below, you end up with a 0.05 to 7.38, but the lower limit is practically 0. What is of interest is really the upper limit, and it was taken for 5% in this one-sided rather than 2.5%. And again, you can do a 5%, 2.5%, or 1% tail, which is rather arbitrary. This has to be recognized. It is up to the designer what should be the probability region. Here is the normalized state estimation error from a single run with a 95% probability region. This is a Q9. It's a high process noise situation. And again, there are 3 points out of 100 outside the 6 region. You can see that sometimes it's low here. It doesn't really matter what's happening there. But around 95% of the points are indeed within the acceptance region, so we can accept the null hypothesis that this filter, which was designed using process noise variance equal to 9 and run on a system with the same process noise, is operating in an acceptable manner. Then next one, we have the Q equals 0. This is a no process noise system. You can see the errors are fairly small, but they are not 0, but they are well within the region, so we don't have any outliers in this case. The Q equal 1, it's a medium process noise. Again, the filter was designed based exactly on the model of the tour system, so we see everything is okay. That's based on a single run. Remember, a single run does not tell us with high confidence that everything is okay. You effectively can lock out in a single run. So, Monte Carlo simulation tests will be shown for 50 Monte Carlo runs. And again, we have a two-dimensional state, 50 runs. The sum before dividing by 50 is 100 degrees of freedom chi-square. So we take the 100 degree of freedom chi-square 2.5 percentile, that's cutting left 2.5% probability, 97.5 percentile cutting right upper tail 2.5% probability. It's about 74 something 130, and dividing by 50, because there's a number of runs, it's as shown before 1.5, 2.6. And we'll come to the figures in a moment. The normalized innovation square, because this is a scalar, you sum over 50 runs, it's a 50 degrees of freedom chi-square. It's lower 2.5%, upper 2.5%, tail 32 something, 71.4, and the acceptance region is 0.65 to 1.43, and the last one will be the sample autocorrelation based on n runs for innovations one step apart, k minus j equal 1. Those innovations should be independent because they are at two different times. In this case, we just take for illustration one step apart. The 95% region will be for minus 2 sigma to plus 2 sigma, because it's Gaussian, or assumed to be approximately Gaussian, and the standard deviation from n runs is exactly 1 over square root of n, that's 0.14. So the minus 2 plus 2 times this quantity is minus 0.28 to plus 0.28. And the figures are here. We see the normalized estimation error squared between 1.5 and 2.6. Pretty much all the points are inside. That's for the two-dimensional state vector from 50 runs. again, divided by 50, you will always look at the region around nx. That's the number of components of the state vector 2. For the normalized innovation square, we have the region centered at 1. It is from 0.64 something to 1.4 something. You can see about 3 points are just about at the boundary. So again, from these 50 runs, we confirm that the filter is operating as intended. Namely, it is statistically consistent. It gives acceptable results. This is the autocorrelation of the innovation, one step apart. It should be 0. Again, some statistical quantity that should be 0 will never give you exactly the same result as the theory has, because you use a finite number of runs. From 50 runs, you get something close to 0. How close? That's exactly what our acceptance region tells you. It should be close enough to 0, and close enough means roughly from minus 0.3 to plus 0.3. And if you go to more runs, obviously you would end up from 10,000 runs, you would have 1 over 100, the standard deviation. So plus minus 0.02 will be the region. You need a very large number of runs. This is as much as we can achieve from the 50 runs. And again, a few points are outside, but most of the approximately 95% are inside. Therefore, we can accept the hypothesis that the filter is operating as intended. The next problem to consider is consistency of the state estimator for a dynamic system. Filter consistency. When we're estimating a parameter which is constant, the definition of consistency for such a static estimator was convergence of the estimate to the true value. This implies that there is a steadily increasing amount of information in the sense of Fisher about the parameter we are estimating, which eventually asymptotically will reduce to 0 the uncertainty about its true value. When estimating the state of a dynamic system, because it keeps varying, we cannot expect convergence of the estimate. What we have is a current estimate, x hat kk, and an associate covariance matrix, pkk. First, before discussing consistency, which is the counterpart of convergence, we'll take a look at the opposite of convergence, that's divergence, because historically it has been observed that the filter used to yield in some cases unacceptable large state estimation errors. And this can be due to one or more of the following reasons. You can have modeling errors, you can have numerical errors, and last but not least, you can have programming errors. The question of what an acceptable estimation error will be from a statistical point of view is what we are going to discuss in detail next. If we are operating under the linear Gaussian assumption, the conditional PDF of the state at time k, p of xk given z super k, is Gaussian with argument xk, mean x hat kk, and covariance pkk. What we do to obtain this estimate and covariance, we use a system model that consists of dynamic equation, the measurement equation, and the statistical properties of the random variables entering into these equations. Again, that's the initial description of the state, its initial PDF, or mean and covariance, the process noise, moments, mean 0 and covariance, and the measurement noise, mean, again, assume 0 and its covariance. If all these are completely accurate, then this density holds exactly. However, we have to recognize that all models contain some approximations in practice. Therefore, we would like to see how, to what extent we can verify this in a practical manner. So, the practical evaluation of consistency is as follows. What we do is we design a filter based on statistical characterization of the disturbances, which is done with moments up to second order. And then we hope that the resulting filter will give approximate first and second order moments of the state. We will use the first moment condition in a slightly different fashion, essentially saying that the mean of the error is 0, which means the estimate is the conditional mean of the state, and the covariance of this state, or the covariance of the estimation error, is as calculated